intern in the audio group this summer. He is a third-year PhD student in the Department of Computer Science and Engineering in University of California in San Diego. His research focuses on developing transfer learning algorithms to improve the robustness of BCI systems. And he also works on developing practical applications using different BCI paradigms. And he is going to present to us the results from his 3-month-long remote internship titled A Closed Loop Adaptive Brain-Computer Interface Framework. Without further ado, Quan-Jung, you have the floor.
By the way, is the meeting recorded right now?
I just started it, yeah.
Okay. So, hello everyone, I'm Quan-Jung. I'm a summer internship in the audio and acoustics research group, working on a brain-computer interface project with my mentor Ivan Tashit. And the title of our project is called A Closed-Loop Adaptive Brain-Computer Interface Framework. And here's the outline for today. I'm going to give some introduction about what is a EEG-based brain-computer interface, and then our proposed framework, then how we set up our experiments to study this topic, and then talk about how we implement the two main components, which are the ErrP classifier and the SSVEP classifier in our framework, then show what we got in this summer, and then the conclusion. So first, brain-computer interface, or BCI, is a system that can translate users' brain activities or users' cognitive states into commands for machines or for computers. And there are multiple brain imaging methods to implement a BCI system. For example, there are some invasive methods that can measure the ECOG or the local field potential or the single unit activities of our brain. But these kind of methods are invasive and they're unlikely to be used by general public. And there are also methods that measures the change of the blood oxygen in our brain tissue. And so the NIRS and the fMRI. However, these kind of methods have slow reaction time because the reaction time of our blood oxygen is relatively slow. So they're unlikely to it's unlikely to build an interactive BCI to have an efficient interaction between the user and the system using this kind of method. And not to mention the fMRI requires a huge magnetics, so which is usually only be able to be done in a laboratory. So in this study, we focus on using the EEG to decode the brain. So the EEG measures the voltage fluctuation from the ion current within the neuron of the brain, and we can measure the EEG simply by putting electrodes on our scope to measure the change of the electric field between these electrodes. So we believe the EEG is the most suitable brain imaging methods to implement a real-world BCI because first, it has relative higher temporal resolution to give the possibility of having a efficient interaction between the user and the system, and also it has relative better portability. So to allow user to actually wear it during their daily life. So for example, people have already tried to combine those EEG electrodes with some hardwares people have already been wearing, like glasses or VR headsets. So there are actually multiple types of EEG-based BCI. There's something called passive BCI, basically monitor users' cognitive states, like workload or sleep stages, etc. And there are also something called interactive BCIs. That is basically a BCI system that allows user to voluntarily control the BCI system. And in this study, we focus on the BCI system, which is based on something called steady-state visual evoked potentials. So the steady-state visual evoked potential, or SSVEP, are basically the brain responses to some repetitive visual stimulation. For example, we can build a virtual dialing keyboard that each digit in this keyboard is flickering at different frequency. If, for example, the digit 4 is flickering at 10 Hertz, and if a user using this dialing board intends to dial number 4, then he or she can stare at this digit, and the 10 Hertz flickering can induce certain responses, basically the 10 Hertz or its harmonic responses in this user's visual area. So a BCI system could detect that these kind of brain responses and know that this user is intending to dial 4 in this case. So although EEG-based BCI is the most suitable for real-world application, it still suffers some problem. And one of the biggest problems is that EEG has a large variability, especially in the cross-subject scenario. So different subjects or different users have very unique patterns in their EEG signals. It could be due to different users have different cortex shapes or the scope shape, and different users can have different background activities because those things in their mind are very different. And EEG also has relative smaller cross-section variability even within a single individual. And it's mainly due to there's always a displacement between each time when the headset is set up. Also, the scope conductance will be different every day. Depends on the condition of our scope. So in order to build a robust BCI, most BCI systems require users to go through a calibration process every time before use, so that the statistical model in this system can be optimized to have a robust performance. And the problem of having this calibration process is this process is usually very time consuming, which will greatly drive people from using this kind of system in their life. So people have also tried to propose using transfer learning techniques to reduce the calibration process. So the main idea of using this kind of transfer learning techniques is that we can utilize some existing data, either from old users or from the same users, but from previous days or previous sessions, so that we can train a model based on these existing data sets. And then we only need a small amount of additional calibration trials before use to fine-tune this model. But the problem is this kind of system still require some calibration trials. So it's still not fully plug and play. And that's why we're proposing to use some adaptive models that that allow the BCI system to start from using an initial model that is trained with some existing data. And then this model can be updated and improved during the time the system is being used. So the system can be plug and play, and during the time the user is using this system, the BCI system can collect new testing trials to update the model. And the big advantage of this kind of adaptive model is that it can make the system become plug and play, and also you can capture the changes of the signals. For example, over the time, this user can get fatigues, or their intrinsic brain activities could change over time. And by including the new testing trials, we could be able to capture these kind of changes. But the problem is, how can we obtain those labels for those incoming new testing trials to actually fine-tune the discriminative models used in the BCI system? So it leads to our proposed framework, the closed-loop adaptive BCI framework. And so first, I'm going to introduce there's a kind of EEG response called error-related potential. So error-related potentials, or ErrP, happen when a user observes some unexpected outcome. So in this study, we're focusing on interaction ErrP because in our targeting scenario, the user is controlling a certain type of BCI, and the BCI will generate some output to the user. So the user will observe those output, and if the output does not match the user's expectation or intention, there will be a ErrP induced in the user's brain. So if there's no ErrP detected when the outcome is shown to a user, it means that that predicted label is very likely to be correct. So we can include that predicted label and the corresponding trial back to the classifier to improve the original BCI classifier. So here's the full system diagram of our framework. We have a user interacting with the BCI system, mainly with his or her SSVEPs, and we have a SSV classifier decode the SSVEP and generate some result, and then these results will be displayed to the user to further induce the error-related potential of this user. So we can have an error detector to observe the EEG response during the period of the user observing these results, and to see whether there's a ErrP detected, and then feedback this pseudo label back into the SSVEP classifier to improve or adaptively fine-tune this classifier. So as you can see, there are two main components in our framework. The first one will be the SSVEP classifier, and the reason we chose this BCI because it's a well-studied and a classic one, so that we can focus more on the effect of the whole system instead. And we chose to use a three-way classifier to meet the generality. Also, studies have shown that in order to have a best performance, to obtain a best performance of an SSVEP classifier, a calibration process is usually required. So it means that we can use our adaptive framework to reduce this kind of calibration process. And the second component will be the ErrP detector. It tells whether the predicted SSVEP label is correct to the user or not. And a key feature of this ErrP detector is that it should take short or even zero calibration process, because if it takes a long calibration process, it kind of loses the original purpose of the adaptive model, because we want to make the system plug and play. Fortunately, decent performance of the cross-section or cross-subject scenario prediction have been reported. So, which means we can have we don't need the calibration process for ErrP detector, but we can still be able to obtain a decent performance. And in Temporal, our system will work as following. So it will start with a queue to let the user know the user can start to interact with the BCI system. So you'll mainly the BCI system will have some flickering stimuli to the user, and the user interact with his or her SSVEP responses, and the SSV classifier generates some prediction of these EEG signals, and then these predicted labels will be displayed to the user to further potentially induce the error-related potential. So the ErrP detector can tell us whether the predicted label is correct or not, and then feedback this information to the SSVEP classifier. And so we're expecting that with our adaptive model, a BCI system can have a pre-trained model first. So the model is pre-trained from some existing data, and then this model can be fine-tuned, and the performance of the model will grow over the time the system is being used. So traditionally, if a non-adaptive framework is used, so a BCI system will require the user to go through a calibration process. And during this time, the system is totally not usable. And after that, will be calibrated and then fixed. So it should have a fixed performance after the calibration process. And however, in practice, the performance could decay because there will be changes in the quality of the EEG signals due to the users getting fatigue or some other issue. So we're expecting that with our adaptive model, the BCI system can start from the pre-trained model, and the performance of this model will grow along the time the system is being used, and then eventually become having comparable performance as the fully calibrated model. So next, I'm going to talk about how we set up our experiment. So in this study, we use the EEG headset called ErrP Express Twist from Brim Products. It has 32 channels plus the ground and the reference channel. And we also added one auxiliary channel for a photo sensor to synchronize the timing between the EEG signals and the actual stimulation. And this EEG headset uses active dry electrodes. The amplifier uses a Bluetooth connection to communicate with the laptop. And as for the software, we're using the recorder from the Brim product to communicate with the amplifier, and we have a Unity program that actually display the visual stimuli, and there's a Python script that actually record those signals and save into files or process those signals during the experiment. And we also use the internet protocol called last streaming layer to broadcast the EEG signals from the recorder and also to fulfill the inter-process communication between the Unity program and the Python scripts. And here's a short demo video of how what our experiment process is. So later on, you'll see 3 visual stimuli down here, and each target will flicker in different frequency. And in the beginning of each trial, there will be a red arrow pointing one of the 3 targets, and the participant is asked to gaze at the pointed target during the following period. And after the flickering duration, of the flickering period, there'll be the system will process the SSVEP signals in real time, and then it's an output. So the output will display in the middle, and also the predicted target will be highlighted in green color. And you'll also notice that there's a square at the top here, changing between black and white. So this is the trigger for the photo sensor for timing synchronization. So you see the red arrow, it means the user has to stare at this one, and there's a result. So that trial is correct, and the result left. So this trial is correct as well. And the final one is the incorrect one. So arrow pointing this, but the output, the classifier predict the label as the left one. And so in the last trial, when the user is staring at the visual stimulation, the ErrP response should be induced in this user's brain.
Just one more comment to the audience. In reality, the flickering of the buttons is much faster. It's not that slow, but this is actually the beating between the frame rate and of Teams, and this is why it looks very slow.
Yeah, I'll talk about the actual flickering frequency later on.
Can I ask a question real quick? Are you taking questions?
Yeah, please.
I was just curious if the error response that you see that because the green highlighting is not where they're looking, is it a visual thing, or is it more like a mental thing where it's incorrect and that causes a response that you can measure no matter how the UI was shown?
It could be a mix. So, I mean, even the potential is induced by the visual effect. I mean, the system could still work because you can always have these kind of feedback visual stimulation to the user, but we during experiment the participant is not asked to to really stare at the target, so we believe their ErrP could be actually induced by the fact that the result is not as they're expecting.
Okay, great, thank you.
Okay, so so the data set we have, so due to the COVID-19, I'm mainly the participant that is for the study, and I have 8 cross-section recording in total. So during these sessions, that the SSVEP was classified during the experiment. So for each session here, there was a SSVEP model trained with the data in the previous session, and during the experiment, the SSVEP in the current session were classified by this pre-trained model, and then so that the error-related potential could be induced during the experiment, and both of the SSV trials and the ErrP trials were recorded, and but the ErrP trials were processed in offline, and I also had two more sessions that were fully online, which means both of the SSV trials and the ErrP trials were processed and classified during the experiment, so that the adaptive model could be fine-tuned during the experiment. And yeah, I would like to highlight that the simulated ErrP here means that we had some pilot session that we use the fake SSVEP classifier instead. So the fake SSV classifier basically output the true label with 0.7 probability and 0.37 probability. The fake classifier return the false label. And I also had the second subject, which is my roommate. So we are doing experiment in the same household to avoid the infection of the COVID-19. So for this subject, the first session will be under cross-subject scenario that because by that time the data I had were only from myself. So there was a model pre-trained with my data, and then classify my roommate's SSVEP during the experiment. And after that, the second and the third session, the pre-trained model was trained on his data, so it was cross-session in these two sessions. Okay, so now I'm going to talk about the ErrP classifier, how we process it and how we build the classifier. So first, from literature, we know that the error-related potential mainly locate around the CZ area. So we were extracting the channels from these channels, basically around the CZ and some backward. Yeah, and we did also include the channel around the visual area here, and these signals we reference to the channel behind the ear. to reduce some intrinsic brain activities. The signal, we apply 1 to 10 hertz bandpass filter. As you can see, the ErrP responses are relatively slow. And finally, the signals were downsampled to 250 hertz. And here are some example plot of the average trials within a session. So at CZ and FZ. So we can see that for the average trial, we can easily distinguish them visually. And so after the preprocessing, the ErrP trials were further applied with some spatial filters to enhance the signal to noise ratio. So a spatial filter is basically some linear coefficient for each channel. So if we write the matrix of the data of the sample of each trial as the matrix with a dimension number of channel times number of time, we can calculate the summation of the covariance matrix of all the error trials and all the trials no matter the label. And then after this, we can write the optimization problem to obtain the best weight factor to optimize the variance after projecting the signal into some common spaces. And so this optimization problem is very similar to like PCA or the linear discriminant analysis. And so the answer of this problem is very well known. So the optimal weight factor will be the eigenvectors of this matrix. So the final spatial filter will be the eigenvectors we preserve and then concatenate them together depending on how many components we want to preserve. In this study, we preserve the first 4 eigenvectors of this matrix. So after obtaining this spatial filter, each trial is then projected into the component spaces as the this form. So we multiply the transpose of W with each trial to project this trial into the dimension of number of component times number of timestamps. And after obtaining the time series in the component space, these components were further divided into 2 windows to capture the 2 unique signature peaks. And within one window, so all the windows of all the trials were fed into the linear discriminant analysis. And then so the window of each trial is projected further to the LDA space. So to obtain one feature value in one window. So the first component will generate 2 feature value for 2 windows, and since we are preserving 4 components, so we have 8 feature value in total, and these feature value then will be fed into the classic logistic regression classifier to generate the final prediction. And then I'm going to talk about how we process and build a model for the SSVEP signals. So instead of having a channel around the CZ area, we extract the channel around the occipital area because from literature we know that the facial responses signals are mainly processed in the occipital area. So a 6 to 40 hertz bandpass filter was applied because our targeting frequency were 7.5 hertz, 10 hertz, and 12 hertz, and we want to preserve up to the third harmonics of these frequency. So the maximum one will be 12 times 3 will be 36. That's why we cut at around 40. And these two plots are the average of the spectrum within each label within an example section. And we can see a clear peak at 7.5 hertz for a 7.5 hertz label. Also, we can see the second harmonic. For example, the 12 hertz has a unique peak here around 24. And so for the SSV classifier, we use the convolution neural network to build a classifier. So for each trial, we have a number of channel times number of timestamps, and then the feature in both channel domain and the temporal domain were extracted by two convolution layer, which was in the previous work. And then after the features were extracted, they were further flattened into a single dimension, and then connected with the fully connected linear layer. Then finally projected into the class spaces, which is the dimension of 3, because we were using a 3-way classifier. And a little more detail about how we design the convolution layer. So we use the first convolution layer to find the spatial filter. It's similar as we want to have some spatial filter in processing the ErrP trials. So we also want to find some linear coefficient for each channel in the SSVEP data. So the kernel size was set to number of channel times 1, so that we can focusing on the linear coefficient for each channel. And then after you convoluted with these kernel, the signals were projected from the channel spaces to component spaces. And then the second layer, we have the height of the kernel as the number of components to preserve all the components. And then in temporal domain, we had a 0.5 second window to extract the temporal signatures for targeting frequency. And then I'm going to show results we got.
Guangzhou, can I ask a quick question?
Yeah.
The input features to your CNN,
Yes.
are those the components by time or the channels by time?
The input, the input in beginning will be channel by time.
Mm-hmm.
But the channel here is actually different from the channel in image processing. So in image processing, we have RGB channel, but instead here it's more similar to the width of the image, or the height of the image, and the RGB channel. The idea of RGB channel here will be only a single channel. That'll be because we only have one trial for each trial, for each sample, so it'll be more comparable as the height of the image and the width of the image is the timestamps. So is that clear?
Yeah, thank you.
Okay, so before I show some results. This allow me to introduce some the evaluation flow used in our study. So the first evaluation flow, we were trying to compare the calibration scheme with our adaptive scheme. So here, for each targeting session, for example, if it is session 2, we use the previous session, which is session 1 in this example, as the pre-training session. So we can obtain a pre-trained model using the data within this session. And then for a targeting session, we further split the data in this session into two parts. The first part will be the calibration data. So it simulates the traditional calibration process that the user has to go through this calibration process. Then after that, the system can be actually used. So with the calibration data here, we can obtain the fully calibrated model by fine-tuning the pre-trained model here. And as for our adaptive model, we further split the calibration data into 4 blocks. So because we want to observe how the performance of our adaptive model grow as a new calibration trial or new online testing trial coming in. So we split this calibration data into 4 blocks, and the adaptive data adaptive data pool was updated block by block. So whenever there's a block coming in, we had a policy to decide whether trials in this block can be added into the adaptive pool. And then so the size of the adaptive pool will grow as more blocks coming in. So the adaptive model can be obtained by fine-tuning the pre-trained model with the adaptive data. And the second evaluation flow is to simulating the online performance. So in this case, we no longer have the fully calibrated model because we want to simulate that the system right now is plug and play. We split the target session into 16 blocks, and so each block is evaluated first as the plug and play system that the trial is immediately evaluated. And after evaluate the model with these trials, then we can make these trial, put them into our adaptive pool to fine-tune to obtain our adaptive model, and then this adaptive model could be used for the next block. So as you can see, the adaptive model is always updated here, and then seeing the new block, and then the trials in this block were further used to fine-tune the model. So the policy of how we add the SSVEP trials into the adaptive data pool is shown here. So whenever an SSV trial and its predicted label and the corresponding ErrP trial come in, we'll first see whether the ErrP detector can confidently classify this ErrP trial. So if so, then we'll see whether the ErrP detected is whether ErrP is detected in this ErrP trial. So if the ErrP is detected, then we can say that the predicted label to this SSVEP trial is probably wrong. So we'll discard the SSV trial and its label because we're having a three-way classifier. So we know the label is not correct, but we have no clue about the actual label of that. But if the ErrP is not detected, then we have a confidence that this predicted label is correct. So we can further add that SSV trial and the pseudo label to the adaptive pool to fine-tune the model. And here's the performance of our ErrP detector. We can see that after applying the confidence threshold, we can further boost the performance of our ErrP detector while still preserving a decent amount of the trials. And the good thing of this model is that we have a very low false rate here, which means when the ErrP detector tells us that the predicted label is correct, it is very likely that it is true. So it means that we are not adding trials with wrong label in our training data. So if we're adding wrong label into the training pool, we can easily ruin the model. But with the relative lower false negative rate, although we are missing some trials because of the false positive here, but we can avoid the risk of ruining the model. And here's the result of the classification of the SSVEP trials of the cross-section recording subject 1. We had multiple simulated model to compare. So the pre-trained model, we talked about that. This is just trained with the data from previous session. And the fully calibrated one is further fine-tune the pre-trained model with all the calibration trials and labels. And the curve with is similar to the fully calibrated one, but instead of adding all the calibration trials and labels like all together, these trials are progressively adding to the training pool, following the block design we have. And the perfect ErrP is assuming the ErrP detector is perfect, having the 100% accuracy. And the semi-supervised here means we're adding those trials in the pseudo label. The pseudo label were not determined by the ErrP detector, but determined simply by its predicted classes instead. And the adaptive model is our proposed method. And we can see that in the evaluation 1, the performance of our adaptive model is as what we are expecting, that it grows from the pre-trained one to the gradually converge to the fully calibrated one. And the bar plot here shows the statistics of the accuracy at the last block. And the p-value here are the Wilcoxon sign rank test between the adaptive model and the pre-trained model here over 8 sessions, and the p-value is smaller than 0.05, which means that our adaptive model kind of consistently outperform the pre-trained one over these 8 sessions. And if in the evaluation 2, we can see that the adaptive model and outperform the pre-trained model, especially at later blocks. So especially when the adaptive model is fine-tuned with a certain amount of blocks. Also, yeah, you can see that with the true label, the performance is mostly the best one across time. And here are the results of the cross-subject scenario of subject 2. So in this one, the growth of our adaptive model is less observable. Like in here, if we only have 4 blocks to adapt, it's hard to tell the trend of whether our adaptive model can actually outperform the pre-trained one. But if we have longer, if we have larger number of blocks to adapt, we can kind of see that this adaptive model gradually diverge with the pre-trained model. Although in the last block, it kind of bounced back here. But we think that this phenomenon is basically due to that we have far worse performance in our ErrP detector in this cross-subject scenario. So it means that we are adding some incorrect label to our trials, so that in average, if we are adding more correct labels into a adaptive pool, I mean, in average, the accuracy can still grow, but it will be less efficient. And here are the cross-section results of the subject 2. Since we only have 2 sessions, we can't do the statistical test. But we can see that in these 2 sessions, especially when we have larger number of blocks to adapt, the performance of the adaptive model clearly diverge, I mean, outperform the pre-trained model. And also note that for subject 2, the subject 2 had worse performance than the subject 1 in general, but the trend remained similar, so that we can say that we can know that the effect of our adaptive framework can work no matter the starting performance of the pre-trained model. I mean, at least in these 2 subjects, we can see this effect. And finally, here's the fully online recording of the subject 1. So in this setting, the ErrP trials were classified and the model was fine-tuned during the experiment online. And so we had the labels during the experiment recorded, and also we are comparing our adaptive model to the case that when the pre-trained model were used instead. And we can see that in the first session here, both models performed very well. So they kind of saturated, and actually much room to improve. But for the second session, we can see that the pre-trained model has worse performance, and the adaptive model can correct this problem and to have a better performance. And especially at the later half of the experiment, the adaptive model managed to maintain a decent performance here. And
just on Jung,
yeah.
We have a question.
Yeah.
Neil?
Yes. Sorry, just quick question for clarification. So in this plot here, green is showing the actual results from the adaptive online adaptation.
Yes.
And red is showing kind of simulated performance based on using the predicted pre-trained model.
Yes, yes.
Okay, great. Thank you.
Okay. Finally, here's a short demo video of how these fully online session went. And so you can see this is me wearing the EEG cap, the photo sensor, the extending box, and the amplifier here. And here are the 3 targets, and the arrow pointing the middle one as the Q. And due to the color effect here, it's kind of hard to see the predicted result, but I think it's a bit laggy, but you can see that the result will be highlighted in green color.
The predicted button is green.
Yeah, the green one here. The green one. Okay, so in the video, yeah, these are 11 from 11 correct prediction in streak. Oh wait, did I? Can you still see my screen?
It's black, Conjunct. You still see the video.
Yeah, so finally, the conclusion. So we showed that our adaptive framework can really make the model improve over time. Also, so it works well. It worked well in a cross-section scenario within the same subject, but the performance in the cross-subject scenario was kind of limited by the ErrP detector. And we also show the demo video, and that we can successfully implement this framework online, end-to-end. And I think the immediate future work will be recording more data to validate the consistency of our work. And so that's my intern project, and I would like to give a special thanks to my mentor Ivan Tashiv. Also, thanks to the members in the MSR BCI team, Andy, Dimitra, David, Ed, Hannes, Mihai, and the other intern Winko. That you gave me very useful feedback either during the meeting or sharing ideas with email or in the Teams chat. Yeah, it's very nice. My pleasure to work with you. Thanks for all your listening.
Thank you, Kwanjong. Thank you. Let's give him a clap. Questions, colleagues? Niall?
Yes, great presentation. So I just wanted to ask how much of this work is related to your PhD work going forward? Since it seems you're in year 3, I was wondering kind of what your next steps were.
Yeah, so in my lab, like Ivan introduced, I focus on building the transfer learning techniques. So, well, the next step could be, combining the transfer learning techniques I already have with this framework. So in here we use, well, the model is based on the convolution neural network, and it has some gradient descent to adapt. Well, we had another time types of model which were based on like some nearest neighbor classifier, something like that. So yeah, I think you will be interested to look into like how we can combine those two.
Awesome, thank you. And I don't want to take up a lot of time, but I just want to mention, funny enough, this presentation or your internship presentation is very similar to my PhD. So if you have any questions or would like feedback on specific things, let me know.
What's really actually?
Oh, sorry. Yes, I'll message you after.
Can you leave your email or something? I mean, or
Now talk with me and I'll connect you with Quan Jung with his
Okay.
university email.
Perfect. Thank you.
yeah, my email is shown here, so yeah, but I mean I don't know your contact information, so
That's fine. I'll reach out then. Thank you.
okay, thank you.
More questions?
Quan Jung, I have a few questions. I'll ask one and see if anyone else has a question in the meantime. If you go back to maybe slide 38 towards the end, the calibration time, you mentioned you have blocks, 4 blocks or 8 blocks or 16 blocks. How much time is that roughly for calibration?
So each block is 18 trials. So in each trial is around 4 seconds in total. So that'll be so one block 18 trial times 4, like 1 minute, around 1 minute and 12 seconds for each block. So it'll be like 4 minutes here, 8 minutes here. But yeah, kind of. So the actual time can be further shrinkage if you know, because I left some space for after the ErrP response, I add some blank for the subject to have a quick to have a quick rest.
Thank you.
But you also increase if you have more number of targets. So it kind of depends on what kind of BCI you're building.
So if you compare this slide with, I believe was the next one, subject 2, right, does that show that subject 2, when you train on subject 2's data, the accuracy wasn't as high as when you trained on your data and tested on subject 2? So basically, you were able to compensate for subject 2's low accuracy by training on a different subject, subject 1.
So I believe there's the variation here every time when the headset is put on this subject. So when I myself was the participant, I mean, I can better control the EEG headset. So this, well, I guess they'll be more robust when I put on myself, that I know the limitation of how much pain I can I can endure, and like how deep the electrode can be put. But yeah, for information, the EEG headset we use does not tell the impedance of the electrode, so I kind of have to visually observe whether the signal quality was good enough. And so when setting up on my roommate, I guess there's more variation when putting on devices. Also, I myself has a lot more BCI experience. So the BCI thing is actually a skill. You have to learn how to, once you are more familiar with using this kind of system, you can have better accuracy. And so for him, he's a non-experienced person, and kind of I think his signal quality or the capability of him getting induced by the visual flickering kind of varies a lot more than me. So I can't draw the conclusion, like statistical conclusion, that train with the data on myself rather than train the data of himself can really bring better accuracy.
It's this variability can be even from insufficient data. We'll have to get 10, 15, 20 subjects to make some more definite conclusions, I think.
Yeah.
More questions, colleagues? No more questions? Last chance? Okay.
I'll take one.
Oh, go ahead.
Yeah. So you've after all you've done with ErrP, ErrP, do you think that it's the right approach? Do you think that of all the things that we could sense, do you think that that's the one to go with?
So I believe it'll be one of the good reinforcement signals for building this kind of framework. And I think it's actually, wait, do I lose my sharing?
No, we see it.
But let me so. So here, there's a semi-supervised thing here. I believe it's actually better to combine these two. So sometimes you have very strong confidence just simply from your original classifier that your result is correct. And so I believe, so that kind of give us an independent information. So we can say that the information we can obtain from the ErrP is kind of independent from the information we can obtain from the classifier, because the confidence of these two models are independent. And I think it kind of leads to a more fundamental learning problem that, so if you have a new trial coming in, if you originally, without the ErrP detector, if you are building a semi-supervised model, you originally have a very strong confidence that your label is correct. So maybe adding this new trial will not be very helpful because you are not pushing your classification margin further. So with this ErrP response, you can add some trial that originally your model is not so sure about the correctness of this label. So adding this, but if your ErrP trial is your ErrP detector is very confident, then you can kind of greatly move your margin or your like classification hyperplane or something like that to a better place. So I believe it's better to combining these two. And also, I think it'll be a good future topic that if you are confident in your classifier in the first stage, then you can probably use that confidence to further fine-tune your ErrP detector. So they'll be bidirectional, fine-tuning each other. And so, although besides from this adaptive learning problem, I mean, adding the ErrP detector has actually another big advantage is that you can correct your prediction. So we didn't implement that because we're not discussing about that. But if you detect some error, you can actually try to correct that. Like if you have a binary label classifier. So I believe like adding this ErrP component in your framework is definitely a good way to go.
Aren't there cases though where like ErrP and SSVEP fail at the same time? You said they're independent, but wouldn't there be situations where both of them would fail?
Yeah, there definitely might be, but then in that case you kind of
You're hosed.
If your mask falls from out of your head,
Yeah.
yes, they both will fail.
Your host. Yeah. Okay. Thanks. It's a great presentation. Thank you very much.
Thank you.
More questions, colleagues?
One generic one. What is your sense, Kwang Jung, if you for the cross-session training, if you had more original training data, would that help, or do you think it might be better to have, let's say, lots of not so great quality data, or maybe 1-2 great subjects and use that to train your model and then transfer?
Well, I believe, I mean, in average, probably having more subject is better, because so if you have a very good signal quality within a single subject, you might be overfitting on that type. I mean, on that subject or all the subjects similar to that one. But if you have other subject that has larger subject variability, I mean, I having more subject and you kind of have a voting mechanism or ensemble way will be better than having a single subject with good signal quality.
Yeah, I guess what I'm thinking is, until COVID, it was easy to collect people's data in the lab and make sure that the same person puts on the cap and everything is great. But now with COVID, we might have to collect data by sending around the cap, so there might be much larger variability in the quality. That's what I'm wondering. But yeah, okay. I guess we won't know until we try.
Yeah, I think.
But Hannes, this is exactly the variability we would like to address in this with this project, because let's say assume you target a device for BCI for the general population, you cannot guarantee that everybody will put the device exactly the same way with medical precision as experienced technician will do. So that's actually a good thing.
Right. Yeah. I guess I guess the current hardware is not really made for, how should I say? It feels like with the current hardware is sufficiently complex that you might get no signal at all if you don't know how to put it on. Whereas maybe if something were to be handed to a consumer, there should be much less room for error than there currently might be with the current hardware.
Absolutely. No one of us imagines that the future BCI users are going to wear EEG caps.
Yeah.
Yeah, also I think a good design for if you're doing some like keep swapping user, then probably using some disposal electrode will be better, because I think people will feel uncomfortable when use some electrode that's being used by many subjects already. Like the brand, like the smarting thing with the sponge, it's disposable. Probably it's better for swiping users. But
Yeah, thank you.
More questions? Thoughts, comments, feedback?
Well, I must say that you're deciding during test time. Your latency is just 1 or 2 seconds, which is pretty great. From the video you showed.
thank you.
That is wonderful.
Thank you, Dimitra. More comments, questions, feedback? If not, let's thank Quan Jung again for the wonderful talk and the discussion to start. Thank you, Quan Jung, and thank you all for joining us for this talk. Quan Jung, don't forget before to exit the Teams meeting to copy and paste the contact information Neil provided.
Okay.
Thank you all for coming, and in a week or so, this talk will be available for viewing publicly outside of Microsoft Corporation, and I think in a couple of days it will be viewable internally from our website. Thank you for coming. Bye.